So, you may remember that around last winter there was a lot of buzz in the popular science media about the story that Earth may have once had planetary rings like Saturn. And that's a very buzzworthy story. It's a very compelling image, and there's already been a lot of great paleo art about it. In specific, the study in question is the rather straightforwardly named Evidence that Earth Had a Ring in the Ordovician by Tompkins, Martin, and Kaywood, published in November of 2024. The paper is open access, and it maybe gets a bit technical at some points, but you should be able to follow the main ideas if you want to look it over. I'm World Building Pasta, by the way. Mostly I write a blog talking about how you can create fantasy worlds with realistic geology and that sort of thing, but for my first video I wanted to look at this paper and a bit more generally about how these sorts of studies are presented in the media. So, in short, the paper begins with the observation that there's a period of increased meteorite impacts throughout the late Ordovician, from about 470 to 440 million years ago. We can see this in the geological record, both in terms of a larger number of large impact craters and as greater amounts of small bits of meteorite material and sediment from that time. That material is all of pretty uniform composition, which suggests to us that this all came from a single source body rather than a bunch of different random objects from the asteroid belt. The rate at which this material appears in the geological record starts as this sudden peak at around 466 million years ago, and then it gradually declines over the following million years until it returns to more or less background levels a bit after the end of the Ordovician. This has all been noted before, and some previous studies have suggested that there might have been a single large asteroid in the belt which broke up and sort of sent this shower of debris throughout the solar system that then declined over time. There's nuances to that proposal, but at any rate, these observations about increased meteorite impacts already have potential explanations that this paper doesn't specifically refute or confirm. Instead, the main new observation brought forward by this paper is that, based on reconstructions of tectonic motion since then, all of the 21 large impact craters with reasonably well-constrained ages within this period would have all been within about 35 degrees latitude of the equator when they formed. Now that's interesting, because if all of these impactors came from objects that independently encountered Earth, we would expect them to fall essentially randomly all across the surface of the globe. So if we can take these 21 large craters as a representative sample of all the actual impacts that happened in that period, it would be vanishingly unlikely for so many of them to randomly fall within this narrow range of latitudes. The researchers therefore propose that these aren't all independent bodies. Instead, they think that a single large body, perhaps but not necessarily from that single large asteroid in the asteroid belt, was captured into orbit of Earth, passed under its Roche limit, and was torn apart by tidal forces to form a ring of debris around the planet. Tidal interactions with Earth would have caused this debris to fairly quickly shift into a low circular orbit over the equator. Planetary rings, like Saturn, and then orbital migration and drag from the upper atmosphere would have caused it to fall down to the surface over time. First a lot of material, and then declining over time as the ring is depleted of material, basically. This material would all tend to fall down near the equator, and it would be of uniform composition, so that all matches up pretty well with the geological evidence. The paper also suggests that a planetary ring could have significantly shaded the Earth's surface, contributing to a trend towards a cooler climate across the late Ordovician. Now, I want to emphasize suggest there, because there's a nuance here which is often lost in the way that scientific studies are presented in the popular media. Papers like this often have a specific hypothesis that they want to test and investigate, and that's where they draw their main conclusions from. But then, in the discussion section, they'll talk about other potential implications of these conclusions or suggestions for future papers to investigate. In this case, I think the link to the Ordovician cooling is a bit more than a passing suggestion. They seem to say that maybe it would even strengthen the ring hypothesis, because if you can explain both the geological record and the cooling climate with the same mechanism, then that's maybe a bit more parsimonious than saying that these were caused by two different things. But still, it's ultimately more something they suggest for future research than something they really demonstrate on their own. They don't do any sort of climate modeling of the scenario or anything like that. So I think a lot of the attraction of this idea is just sort of on conceptual and aesthetic grounds. People have been wondering for a while what it would be like if Earth had rings, and the Ordovician, I think, feels to modern eyes like this very alien period. You had all these bizarre, enormous mollusks and arthropods, and life is sort of just starting to crawl into land. The most familiar animal to us would be a jawless fish with primitive fins. So it kind of already feels like an alien planet, and having rings in addition to all of that just sort of feels appropriate in a way. But approaching this idea just on purely scientific and objective terms, the paper does make a fairly decent argument, and it backs it up with a lot of pretty compelling statistics. I'll even say that I don't see any particular reason that planetary rings couldn't form in this way. The paper doesn't do any sort of astrophysical modeling, but in broad strokes, the idea of a large body getting captured into orbit of Earth and then undergoing tidal disruption, forming a ring system, that's all a pretty plausible scenario. We would even expect, then, that such a ring would gradually disperse, with some material falling to the surface. All of that said, I do have some doubts that the evidence they present in this paper really points to this specific scenario. So first off, you may have caught that point, that in order to say that the record of impact craters from the Ordovician shows that there was a bias towards only equatorial impacts at the time, we have to be able to assume that this record of craters is a representative sample of all the actual impacts that happened in the late Ordovician. You know, it could be that really there were a lot of impacts that happened all over the planet, but for some reason, only the ones at low latitude were preserved and survive to today. Now, of course, the authors are aware of this. Any statistical geology is always going to have to deal with the problem of preservation bias. So, the bulk of their actual work on this paper seems to have been spent collecting together data on what the distribution is of surviving rock and sediment that could actually preserve an impact crater from the Ordovician. What they conclude is that there are actually plenty of suitable rocks across all different latitudes at the time. At least in the southern hemisphere. There wasn't much land in the high northern latitudes in the Ordovician, and no ocean crust has survived from that period. So because of that, the uneven distribution of surviving craters likely does represent an uneven distribution of impacts, they conclude. But that said, let's look at the craters they actually identify in their study. To clarify a bit, this map shows the distribution of continents at 450 million years ago, and then the sort of grayish ghosts behind them show their movement up to that point from 467 million years ago. Each crater is similarly shown with a range of potential points of impact corresponding to the uncertainty of their age. We know where on the continent these craters are, but because the continents were moving and we don't know exactly when these craters formed, we can't say exactly where the impacts happened on Earth's surface. The paper also discusses some competing models of how continents might have been distributed in the Ordovician, but none of it really makes much of a difference to the overall picture. So, looking at the global distribution of craters, you can maybe already see the issue here. Almost all the craters included in the study appear in two large clusters, one in southern Laurentia, now eastern North America, and one in southwest Baltica, now eastern Europe, with the exception of only two craters a bit further north in Laurentia and a single crater in modern Australia. If all of these impacts are from debris falling from a ring over millions of years, they should be concentrated in latitude, it's true, they should all fall near the equator, but they should be randomly distributed in longitude. They should be falling all around the globe along the equator. But instead of that, the surviving sample of craters is pretty clearly biased towards these two continents on the map, while several other large masses along the same latitudes lack craters entirely. Antarctica, of course, could have any number of undiscovered craters under the ice, and these three pieces of modern China have seen pretty extensive tectonic deformation that could have erased any craters. But by the paper's own analysis, Siberia, India, Australia, and parts of Africa that were in the tropics at the time all have plenty of suitably old and undisturbed rock that could have preserved craters. Now, even if this isn't due to some kind of preservation bias, there could still be an identification bias. Surveying and dating of geological features has generally been a lot more comprehensive in North America and Europe than in a lot of these other areas. Because of, history. So, maybe there are more craters in these areas, but they just haven't been found or precisely dated. The paper actually does mention a number of other craters that could be late Ordovician in age, but they haven't been dated that well, so they didn't want to include them in this study. And that does include a few more in Australia, but still not many in Siberia, India, or Africa. But if we accept that there's a potential sampling bias that explains why the craters aren't more evenly distributed in longitude, why couldn't that also explain why they aren't evenly distributed in latitude? Either this is a good enough sample of impact craters that we need to account for how they're distributed geographically in all terms, both latitude and longitude, or it isn't a good enough sample and we can't draw any sort of conclusions from how they're distributed. You can't really have it both ways. That's really my main methodological issue with this paper. They only recognize two possible scenarios. Either all of these craters were formed by debris falling from a ring, or they're a representative sample of a completely random distribution of impacts. And all of their statistical analysis is aimed at distinguishing these two possibilities. The paper speaks at great lengths about the very low probability that independent random impacts from deep space would all be so concentrated in such a narrow range of latitudes, but it says nothing about the probability that independent random impacts from a ring would all be concentrated in such a narrow range of longitudes. They present evidence that the positions of impacts are all correlated to each other, but they don't mention any possible reason for that other than rings. Even if we don't want to attribute this all to some kind of sampling bias, we don't necessarily have to go to rings. In 1992, the comet Schumacher-Levy 9 passed close to Jupiter and underwent tidal disruption, tearing it into, coincidentally, 21 large pieces. But rather than forming a ring, these fragments all fell to the planet's surface 2 years later, forming a string of impacts across Jupiter's surface which disturbed the cloud structure for months afterwards. If something similar happened to a body passing near Earth, it could similarly form a string of impact craters that were all clustered together on the surface rather than randomly distributed in either latitude or longitude. Now, in that case, these craters would all be basically simultaneous in the geological record. The confidence in dating of late Ordovician craters varies, and these things never tend to be very exact. The paper gives this neat chart of reported age ranges, but even many of the limits here shouldn't be taken as too definitive. Suffice it to say, though, that I don't think it's really likely that all of these craters could be related to a single Schumacher-Levy 9-like impact chain, but there are a few clusters in time here which also tend to be clustered together in space, though Laurentian and Baltica were close enough together at the time that a single impact chain could conceivably have stretched across both of them. If even a decent number of these impacts were group events, that shifts the overall statistics of how likely it is that this distribution could form without needing a ring. To be clear, I am just spitballing here, though. I did find one paper suggesting that 2 of the impact craters on Baltica could have come from a single body that broke apart, so there's at least some precedent there in the literature for suggesting that you can get multiple craters from one event, but that's still just 2 craters out of 21. I haven't seen anyone suggesting anything so grand as what I'm applying here about multiple breakup and clustered impact events. So don't take any of this as necessarily a better founded proposal than the rings. Really, just a simple sampling bias is still probably the better alternative hypothesis. My main point here is just that I think the paper sets up this kind of false dilemma between only 2 ways to explain the data, and that shapes the way the statistics works out in a way that strongly favors their hypothesis. I'm not trying to say that they've intentionally misrepresented their data or anything like that, but just because they haven't accounted for a lot of potential confounding factors or considered any alternative scenarios, I don't think the numbers they pull out of their statistical analysis is really all that useful, or they lead directly to the conclusions that they come to. I also think it's worth noting that although a lot of these impacts occurred at low latitudes, a lot still aren't that close to the equator. We generally expect that if you have planetary rings, they're going to be very thin with not much orbital inclination, so naively you would expect that the debris is just going to fall straight down on the equator. But most of the impacts in this sample are well to the south, and those in Baltica particularly are as much as 35 degrees away from the equator. Maybe the influence of the moon complicates the structure of the rings, or maybe there are errors in the way we've reconstructed the position of the continents at the time, and they're actually further north. I don't feel qualified to assess how likely either possibility is, or how exactly debris falling from a ring should be distributed in latitude, but it is a pretty large discrepancy that the paper doesn't really try to explain. They don't do any sort of physical modeling of how material from the ring should fall. Like I said, they do discuss a few different reconstructions of how these continents would have been positioned, but they all place the Baltic impacts pretty far south of the equator. Okay, just a quick editing insert here, because I feel like if I don't explain this properly, it's the first things I'll get questions about. So, why can't we have high inclination rings? Why do they have to be over the equator? The answer comes down to tidal and orbital dynamics, which are scary and complicated, so I'll link to a couple sources that explain this in a bit more detail, but the short version is that any rotating planet is going to be bulged at the equator because of centrifugal forces and all that. And so any object in a low inclined orbit of the planet is going to feel a gravitational tug towards that bulge. It's going to be pulled towards it as it passes above and below the equator. This will reduce its inclination a bit, but the way the orbital dynamics work out, the main thing it'll do is cause orbital precession. The orientation of the object's orbit will shift over time. And the thing is, a ring is composed of many different objects, all on their own slightly different orbits, so they'll all precess at different rates, and so end up in different orientations around the planet. So, rather than staying together as a ring, you quickly end up with just a diffuse cloud of objects, all moving around in different directions. And once they're all chaotically spread out like this, they'll start interacting and colliding with each other, and these interactions will tend to average out their momentum, so they start moving in more similar orbits again. And because that initial orbital precession is symmetric around the planet's equator, things will tend to average out so that the average momentum for the whole cloud is centered on the equatorial plane. So eventually everything will settle down into an equatorial ring. And, even if it isn't perfectly equatorial at first, it'll just disperse out into a cloud again, and this will repeat until sooner or later you do end up with an equatorial ring, which is then a bit more stable. And because the orbital periods are so short, this process should happen very rapidly. Really, you shouldn't even have time to form an inclined ring in the first place. You just go to the diffuse cloud and then quickly collapse into a ring. There's no prolonged period of time where you have pieces of debris at high inclination. And the paper does directly acknowledge this. They think the ring had to be equatorial. They just don't really explain how you then end up with material then wandering off to fall so far south of the equator. There is actually one brief point where they say that the impacts cover a greater range of latitudes earlier on, so maybe they're coming from that initial breakup of material before a ring fully forms, but honestly I'm not seeing it. You're still getting a lot of impacts at 20 to 30 degrees south, tens of millions of years after they say the ring should have initially formed. Also, while I'm at it, some of these craters would have required quite large impactors to form them, and I'm not sure you'd really expect such large pieces to be falling from a ring after that long, but maybe the dynamics are more complicated. I don't think I can say that very confidently. Ultimately, none of this specifically rebukes the possibility that there was a ring in the late Ordovician, even if not all these impacts came from debris from the ring, or there's some significant sampling bias at play. In principle, there still could have been a ring that at least partially contributed to these impacts. But I'm just skeptical of the claim that the evidence they present specifically points to a ring to the exclusion of all reasonable alternatives. Okay, but all of that aside, let's say there were planetary rings in the Ordovician. Could that explain the cooling of the climate at the time and the mass extinction at the end of the Ordovician? Could it even be a better explanation than other alternatives that have been proposed, which then might be a point in favor of there having been rings, even if the evidence from craters is a bit inconclusive? Well, very little research has actually been done on the potential impact on the climate of planetary rings. Based on just simple geometry, if you have rings around the equator of a tilted planet, during the seasonal extremes, they should shade a lot of the winter hemisphere while reflecting a bit of light onto the summer hemisphere. In spring and fall, they'll maybe shade some equatorial regions, but probably that won't have much impact. The patterns of shading across the seasons would be pretty complex. They'd vary across the day and throughout the year, and in a way that doesn't really resemble any other commonly modeled scenario. The paper cites what is, so far as I can tell, the only real attempt to date to model a ring-influenced climate in detail, the 2002 paper Climatic Effects of an Impact-Induced Equatorial Debris Ring by Fawcett and Bosla. Oddly enough, this modeling was done in support of a totally unrelated proposal that debris thrown up by an impact in the Eocene 35 million years ago may have formed a ring that then caused rapid cooling at that point. So far as I can tell, this is an idea that had been floating around since the 80s, but no one else really seems to have picked it up at this point, and it's been effectively forgotten as a geological theory. There have also been occasional suggestions that maybe planetary rings could have contributed to the global snowball events around 600 million years ago, but that's a whole other story. None of the paper's analysis is really specific to any scenario. It's just investigating how much cooling you can get from planetary rings in general. And the answer is actually quite a lot. With rings based on Saturn's rings but scaled to Earth's size, the paper found that the global average temperatures dropped by about 10 degrees Celsius, causing widespread snowfall well into the subtropical regions, and probably encouraging the spread of glaciers in the long run. Bear in mind though, first, this model was run over 20 years ago. Global climate modeling at the time was okay, but it lacked a lot of the detail and complexity of modern modeling, and it was severely limited by the available computing power at the time. Second, because of the limitations of that model, they treat the rings as completely opaque, effectively modeling them as a solid black disk with a hole in the middle that Earth went through. Going by Saturn's example again, the best numbers I could find indicate that the densest parts in the middle of Saturn rings could indeed block over 90% of the light passing through them, but much of the rings will only block around 50 to 80% of the light, and the thinner inner parts would block less than 10%. This is going to vary a lot depending on the exact angle at which the light passes through the rings, but in short, the amount of shading, and therefore the amount of cooling they found in this study is probably not totally outside the realm of physical possibility, but is probably a high estimate for any reasonable scenario. The paper also doesn't model any additional light reflected onto Earth from the rings, but I doubt that that amounts to much. Though, as a point of pedantry, all the art I've seen in relation to the Ordovician ring paper shows bright white rings based on Saturn's, but Saturn rings are mostly composed of water ice, whereas these rings would be mostly composed of rock, and so they'd be more gray like the moon's surface. Though the moon can look pretty light just because it's the brightest object in the night sky against a black background, and the rings would probably also be pretty bright, but just not as white as Saturn's. At any rate, I have heard of some interest from some climate researchers about running a better model of the potential climate impact of rings, specifically in response to this new paper, but that sort of thing takes time. We'll just have to see how it pans out. For now, about the best we can say is that it's probably not out of the question for planetary rings around Earth to cause cooling of about the scale we see in the late Ordovician. But let's take a closer look at that. Going back to this figure, you may have noticed that it helpfully compares the timeline of potentially ring-associated impacts to reconstructions of global average temperatures. These reconstructions are never terribly exact, but you can see the overall trends. From a very hot greenhouse climate in the Cambrian, temperatures start dropping near the start of the Ordovician at around 487 million years ago, and then continue to fall throughout the period, culminating in a sharp drop at the end, which was probably even quicker than this coarse reconstruction shows. This is the end Ordovician mass extinction event. At around 445 million years ago, temperatures suddenly plummet by around 5 degrees C, to a low below even that reached in the depths of the most recent glacial period in our current ice age. As glaciers rapidly expand over the southern hemisphere, sea levels drop, wiping out the warm water, shallow sea ecosystems that have been diversifying since the Cambrian. Then, a million years later, temperatures shoot back up, wiping out all the cold water species that had flourished in the meantime. Altogether, something like 70 to 80% of animal species go extinct, ranking it as perhaps the second worst mass extinction event within the last half-billion years for which we have a good fossil record. Though there's all sorts of nuances to that framing. So, yeah, pretty significant cooling of the sort that we've just seen rings can cause. But I think people can sometimes misunderstand that the way that climate forcings, like the greenhouse effect or levels of sunlight, actually relate to climate change over geological time. We tend to think of warming as some process adding heat to a system, which causes it to accumulate heat and so gradually increase in temperature. Put a frying pan in a warm fire, the pan takes time to warm up as the fire adds heat to it. Cooling is the opposite. Some process removes heat from the system, and that drains its eternal reservoir of heat, and its temperature drops. This lines up pretty well with how current human-caused climate change is playing out. As we keep adding more carbon dioxide to the atmosphere, it slows the rate at which heat can pass through the atmosphere from the surface to escape into space. And so heat starts to accumulate because Earth is losing less heat to space than it's gaining from sunlight. Sunlight isn't affected by CO2 because of the different wavelengths of light involved. As Earth's temperature rises, it should start emitting more heat. So eventually we should reach a new equilibrium where the rate at which it's losing heat into space is exactly the same as the rate at which it's gaining heat. Just as if you put a frying pan in a fire, it will eventually stabilize at some new temperature. Try not to worry too much that the planet is being roasted in a fire in this metaphor. But that process takes time, so we're currently in a non-equilibrium state. Even if CO2 levels stopped rising today and just held steady, temperatures would continue to increase for some time until they eventually stabilized. That process of moving towards equilibrium could take hundreds of years or even thousands of years if you could do additional feedbacks like glacial retreat or geochemical controls on atmospheric CO2 levels. But many cases of climate change in the geological record play out over tens of millions of years. On those timescales, the climate moves towards equilibrium basically instantly. Gradual warming and cooling is caused not by non-equilibrium processes of heat being gained or lost, they're caused by a shift in the equilibrium. Usually this relates to CO2 levels, so we'll take those as an example. CO2 is being constantly added to the atmosphere by volcanic activity, releasing gases dissolved in rock and magma. And CO2 is also being constantly removed from the atmosphere by geochemical weathering processes, where CO2 reacts with water and surface minerals to deposit out as carbonate rocks. The CO2 in the atmosphere today isn't the same CO2 that was in the atmosphere 10 million years ago, but accepting present circumstances, the overall amount of CO2 in the atmosphere hasn't changed too much, because usually these processes of addition and removal are in equilibrium, just like the planet's overall heat loss and gain are in equilibrium. If a large volcanic eruption goes off, it may release a lot of CO2, and so that'll cause temperatures to rise for a while, but eventually CO2 levels should come back down to that equilibrium level, and the climate will return to more or less the state at which it started at. If the overall rate of volcanic activity rises, then the rate of CO2 addition to the atmosphere becomes greater than the rate of CO2 loss, so CO2 level rises and the global temperature increases with it. But higher CO2 levels and a hotter climate cause the rate of weathering reactions to also increase, so that draws more CO2 out of the atmosphere, so eventually you reach a new equilibrium where the rate of CO2 removal is again exactly equal to the rate of CO2 production. But now the CO2 levels have stabilized at a higher level, and so you have a hotter climate. This process of moving towards equilibrium in CO2 levels takes substantially longer than the process for equilibrium heat, so it doesn't really help us with modern climate change, for example, but by geological standards it's still basically instantaneous. To get a steady increase in temperatures for tens of millions of years, you need a steady increase in volcanic activity across that time, which can happen for any number of reasons related to gradual cycles and the nature of Earth's plate tectonics. Tectonic shifts can also influence the rate of geochemical weathering, or they might alter Earth's albedo, the amount of sunlight that it just immediately reflects away rather than absorbing as heat. But the point is, if you look at Earth's climate at any one point in time during these long-term trends of climate change, it will usually be at equilibrium or very close to it. These gradual changes happen because something keeps nudging the climate slightly out of equilibrium, and then the climate shifts to a new equilibrium that might be slightly hotter or cooler. And then that happens again and again and again over millions and millions of years. In case you're wondering, life does have a bit of an influence in all of this. Plants of course absorb CO2 to make sugars, but that CO2 just gets released again when something digests those sugars. So that's mostly a wash. But sometimes an organism can be buried without fully decaying, and that takes some carbon out of circulation. And there's all sorts of ways life can influence the rate of weathering reactions or alter Earth's albedo themselves. But overall, it still seems like geological processes are the dominant control of climate over these long-term timescales. Or, life that isn't burning millions of years of accumulated fossil fuels in a few centuries. So, going back to the Ordovician, The proposal seems to be that a ring would have probably formed at around 466 million years ago, and then gradually dispersed over the next 20 to 40 million years. That explains both the pattern of large impacts and the sudden appearance of meteorite material in the sediment at that time, followed by a gradual decline. In that case, the ring should be densest when it first forms, so that's when it should have the greatest shading effect. This should cause a rapid drop in global temperatures, basically instantly in the geological record. In that 2002 paper we talked about, that 10 degrees Celsius of cooling they found happened within 16 years of starting the model. As the ring then disperses and this shading effect decreases, temperatures should then rise back up again. But if we look back at the late Ordovician climate record, we don't see that rapid cooling. It actually looks like temperatures rise for a bit after that point where they propose the ring forms, but that's subtle enough that I wouldn't read too much into it. The dominant trend is that cooling starts well before the spike in meteorite impacts begins, and then continues at the same rate throughout the whole period, regardless of the impact rate, with the most notable change being the sudden cooling and then warming at the very end of the Ordovician. Now, that sort of rapid change is a lot more congruent with what we expect from a ring forming and then dispersing, but most of the impacts can be confidently dated to well before that point, and the meteorite material in the sediments had also greatly declined by then. I don't know, maybe the picture is more complicated than what I'm imagining. Maybe throughout the lifespan of the ring, there was material that clumped together into larger bodies, and then those later broke apart, and so the density and the shading of the rings varied a lot over time. Maybe it was a very thin ring, or just a collection of objects in more stable orbits that then occasionally collided. And so it wasn't until the end of the Ordovician that you got a substantial ring that formed and then rapidly dispersed in just a million years. But that still doesn't match up very well with any of the geological evidence they're presenting, and I think I'd need to see some detailed astrophysical modeling before I could really buy into any of those scenarios. Basically, I just don't think the pattern of climate change in the late Ordovician actually lines up with the model really that well, to the point that to defend the ring hypothesis, I think you'd have to argue that it actually didn't have much of a climate impact, and it was totally unrelated to the cooling happened at that time. Interestingly enough, in that 2002 paper, they mentioned that if a ring did form in the Eocene 35 million years ago, it couldn't be used to explain cooling at the start of the Oligocene just a couple million years later, because that cooling was too gradual and a ring wouldn't have a delayed effect like that. And then here in this paper, they cite that as an example of the climate effect that a ring could have, but they want to apply that to 20 million years of gradual cooling. Also, because I know some people might be wondering, the impacts themselves may have thrown up some ash and had a bit of a short-term cooling effect, but that's not going to last for more than like a few decades. Again, you can't just remove a bit of heat for a while and expect the planet to stay cold. You have to continuously shift the equilibrium so that the balance of heat gained by the planet to the amount of heat lost by the planet is overall lower. There is a recent proposal that a particularly large impact may have contributed to that rapid cooling at the end of the Ordovician. The idea there is that because the climate was already quite cool, it was more prone to form large glaciers and ice sheets. So you have this relatively short-term cooling caused by the impact itself, and then that encourages rapid expansion of glaciers. So even after all the ash clears, the Earth has a higher albedo from all this extra ice, and then it's absorbing less heat, and so it settles into a colder equilibrium. There's various feedbacks like this, which give Earth's climate a certain stickiness or inertia, so brief climate disturbances can influence the long-term equilibrium to some extent, but that still shows up in the geological record as a rapid shift in climate followed by relative stasis. Rapid onset of a climate forcing like rings doesn't give you gradual cooling or a delayed effect. And for this big impact event to have caused that rapid glaciation, the climate had to already be pretty cold beforehand. So then, why did the climate cool throughout the Ordovician? Well, records of CO2 levels are pretty hazy that far back, but they do seem to show there was some drop in CO2 levels from the Cambrian. Greater activity by plankton and algae in the oceans may have increased rate of CO2 removal, and maybe some early plants were beginning to colonize the land, and that was breaking up rock and soil, and that increases weathering rates. Again, life's complex influences on the overall climate balance. The large continent of Gondwana was also shifting south, which would encourage the formations of large ice sheets over the South Pole, So then, again, that raises Earth's albedo, it absorbs less heat, etc. The cold snap at the end of that period has long been a bit of a mystery, but maybe it was caused by an asteroid impact, or there's some other recent research that points to a large volcanic event in Iran that seems to have occurred at just about the right time in two bursts a million years apart. I mentioned that volcanoes can produce a lot of CO2, which warms the climate, but they can also produce a lot of rock, which will then weather, and that consumes CO2, and that might have the greater effect in the long term depending on where this volcanism occurs in relation to the global climate. And of course, ash released from a volcano can have a cooling effect, and that won't last too long geologically, but it might help spur rapid glacial growth, and so on. So, conceivably, one large volcanic event could cause rapid cooling, and then another could cause rapid warming, just because of slightly different influences on the overall balance of climate factors. There's clearly still a lot of open questions here, but the upshot of it all is that most likely it was a lot of factors that contributed to the Ordovician cooling in various different ways. And really the most we could attribute to a hypothetical ring is that it may have contributed to trends that were already underway at the time that it formed. Also, if you read around about the Ordovician mass extinction event, you might come across the idea that a gamma ray burst caused it. I'm not even going to take the time to address here. That's a whole other topic. The thing is, if you pay attention to these kind of papers and the popular media around them, this kind of thing actually happens a lot. When it comes to our current ice age, for example, look around and you'll find papers saying that maybe it was triggered by a supernova, or maybe it was because movement of the continents shifted around ocean currents, or maybe it was because of formation of the Himalayan plateau, or maybe it was because Earth was passing through these giant interstellar clouds of gas. But if you actually look at Earth's climate over time, we've been on a pretty clear cooling trend for the last 50 million years. These sorts of papers tend to point to an event that might have coincided with the first formation of large ice sheets in the northern hemisphere about 2.58 million years ago, but it's pretty clear that at best any event that happened at the time was just hurrying Earth along towards a climate that it had already been heading towards for a long time and would inevitably reach sooner or later. Say that we went to a swimming pool, and then I got on a high diving board and jumped off, and while I was in the air falling, you shot at me with a little water squirt gun. When I then landed in the water, would you say that shooting the squirt gun at me is the reason that I'm wet? I don't want to put too much of this on the people who wrote these particular papers. The degree to which they attribute the whole course of Earth's climate to one effect varies. Honestly, astrophysicists tend to be the worst offenders here, but whatever. The issue, as per usual, is how this all tends to get framed in the popular media. You know, we like straightforward stories. This thing happened, therefore we get this effect, and the whole history of Earth is just one thing happening after another. A series of quaint, contained stories. But geology isn't really like that. Geology is 100 different stories, 1,000 different stories, all superimposed on each other, all interrelated, all starting and ending at different times and happening at vastly different rates, and always with sequels and prequels and spin-offs and so on. So, why are the current ice ages happening? Well, the influence of other planets causes regular variations in Earth's orbit and rotational orientation, what we call the Milankovitch cycles. These alter the average distribution of sunlight to higher latitudes, causing them to have cooler summers, which allows glaciers to grow, which then raises the albedo, and so further decreases heat absorbed in a vicious cycle. And as the climate cools, the colder ocean surface absorbs more CO2, which reduces atmospheric CO2 levels, and as sea ice blocks the flow of surface waters and meltwater production at the edge of the glaciers, reduces the ocean salinity. This causes worse ocean circulation, so the ocean transports less heat from the equator to higher latitudes, and there's also less vertical circulation in the oceans, so a lot of dissolved CO2 is trapped in deep waters. Meanwhile on land, reduced vegetation cover in the cold climate and greater land area due to the falling sea levels as the glaciers expand also helps raise the planet's albedo, and allows for more mineral dust to be carried in the atmosphere, which also blocks some sunlight and fertilizes the oceans with iron, which increases plankton activity, which absorbs more CO2. But all of this requires that ice sheets can start forming in the first place, which is helped along in the southern hemisphere by the southward drift of Antarctica and its separation from the other continents, which allows for the formation of a circumpolar ocean current ringing the continent, which blocks any transport of heat from higher latitudes, so the continent cools down. And in the northern hemisphere, tectonic uplift in West Greenland creates colder highlands, which also encourage more snowfall and ice accumulation. But to form large glaciers, even in the polar regions, requires a globally cool climate, which is due to declining CO2 levels throughout the Cenozoic, which is caused in large part by the motion of the continents. In addition to a general shifting of land towards the poles, making it easier to form glaciers, numerous collisions between continents but few continental rifting events means that C4 plate boundaries, which have high rates of volcanic outgassing but low rates of weathering, have been replaced by continental plate boundaries, with little volcanic activity but high rates of weathering, and also high plateaus, more prone to form glaciers. And it particularly helps that many of these mountains have formed at lower latitudes, such that locally hot, wet climates can continue to keep weathering rates high even as the global climate cools. These collisions have also created larger continents with drier interiors far from the oceans, which helps both because drier land areas have a higher albedo and because the ocean tends to moderate seasonal temperatures. So these larger interiors have greater temperature variation with colder winters, which causes more snowfall. Fewer C4 plate boundaries also means less production of new ocean crust, so the average age of ocean crust is increasing. An older ocean crust is colder and so denser, and so floats lower in the mantle, making the ocean basins deeper, such that global sea level declines. So again, there's more land area further from the nearest coastline. This continental motion is part of the overall supercontinent cycle, whereby the continents regularly assemble into a single large supercontinent, but formation of subduction zones around the supercontinent and upwelling of the mantle beneath it eventually leads to a new period of rifting and breakup, forming many new C4 plate boundaries, but then this period of rifting passes and the spraying continents eventually run out of empty ocean to move into and are pulled together by growing subduction zones, so collide back together. As CO2 levels have declined, the climate has become not only colder but more variable, because the lower CO2 levels are, the more effect each incremental change in CO2 has on total greenhouse heating, and so minor influences on CO2 like sea surface temperature and deep water circulation can have a greater effect, which makes it easier to get a runaway cooling process that leads to rapid growth of glaciers. CO2 levels are particularly low recently because the sun is getting gradually brighter over its lifetime, increasing sunlight levels on Earth, which sounds like it should make the planet hotter, but again, a warmer climate causes greater removal of CO2 by weathering, so this causes a feedback that instead of allowing the climate to warm, has reduced long-term average CO2 levels as the sun has brightened. And because solar heating is concentrating more towards the tropics, while greenhouse heating is more globally even, that shift towards more solar heating has reduced the temperature of the poles relative to the equator. And again, lower CO2 levels causes greater climate variability and more potential for runaway cooling. And maybe there was also a supernova, which may have caused more cloud formation, which contributed in some way to all of that. There's no one thing that caused the ice ages. The supercontinent cycle probably bears the most responsibility for forcing some amount of overall cooling to happen at some point, but that didn't necessarily have to result in widespread glaciation. Exactly how cold it got and how fast comes down to all of these different influences, all linked together by various feedbacks, so that the exact effect of each factor is contingent on the combined effect of everything else. And the thing is, scientific research and the scientific consensus is kind of the same way. We like simple stories, so popular science news reports and articles like to present every paper as a breakthrough. It's a bold new idea, never heard before, that perfectly solves an outstanding issue, so we can take it now as established fact. And that's basically never true. Every study is building on the ideas and research that preceded it. This Ordovician ring proposal is more novel than most, but the concept that shading from planetary rings could cause cooling of Earth isn't new, nor is the idea that debris from an asteroid breakup could have specifically contributed to the cooling in the Ordovician. Though the paper I'm referring to here thought was more spread out in the solar system rather than in orbit of Earth specifically. More pertinently, no paper proposing a new model is ever the last word on the subject. There are always details to discuss, more avenues of research to be explored. People will suggest new potential alternatives, or they'll present evidence from their field that conflicts with the proposal, or they'll argue over the details of how the statistical analysis was performed. That's honestly like half of science these days. It's just wrangling over stats. But the point is, if a paper like this doesn't get lots of responses and debate, it's because researchers didn't think it was good enough to even be worth addressing in the first place. Science isn't just a collection of established facts. It's a conversation. It's an eternal dialectic. I don't want to say it's all in flux and it could change at any time. No scientific theory can be trusted. The stuff like CO2 causes climate change and humans evolved from apes that you can rest easy on. We already debated and rejected all the alternatives long ago, and at this point we have thousands of data points that all support the same conclusion. I feel like I need to make this one point absolutely clear. When I'm saying that the causes for climate change over geological time are complicated, I am absolutely not saying that humans burning enough fossil fuels to raise CO2 levels by over 50% in the last few centuries is not the overwhelmingly obvious cause for an unprecedented pattern of climate warming. But putting all that aside, there's still a lot of stuff that today is at the frontier of current knowledge and still needs to be hashed out, and that can take a long time. And I understand how this process can be a bit hard to interpret from the outside. So, for example, you'll see things like someone finds a paper saying that the mass extinction at the end of the Cretaceous was actually caused by volcanic activity and not by an asteroid impact. And they'll think, oh wow, I guess the scientific consensus has changed on this matter, but now we know better. Good thing I read this paper. But then, if you look into it further, there was actually another study in response to that, which found that it was the impact that caused the extinction. But then others said no, it was the volcanoes that did it. And then another paper says no, it was the impact. And so on and so on. And then other papers say maybe it was both events in combination, or maybe the asteroid actually helped trigger the volcanic eruptions, or maybe dinosaurs were already in decline by then, so it was easier to kill them off anyway, except no, they weren't, they were doing fine, except yes, they totally were in decline, except maybe they weren't. There is no single paper here which contains the scientific consensus. Even if individual authors are confident in their conclusions, the field as a whole is in a continuing state of debate. Sometimes people will try to write review papers to sum this all up, but even those aren't necessarily without their perspectives, and you kind of have to already be familiar with the subject to be able to spot that kind of bias. So, unless you're willing to track down dozens of papers and try to sort out what the latest word is on any of them, it can be really hard as an outsider to figure out what is the actual consensus on any of this. And the thing is, a lot of papers are kind of written in this context, not to close the book on the subject or find the final answer, but just push the conversation forward. I don't want it to come off like I'm saying like this Ordovician ring proposal was pseudoscience or should never have been put out there. I think the authors probably should have been a little more cautious in their analysis, should have at least mentioned a few more possible confounding factors or potential alternative explanations to their data, but I understand why they didn't feel equipped to dig too deep into the astrophysical or climate aspects of this idea, and maybe they just didn't have the time or the resources to reach out to other researchers to contribute in those areas. They recognized an unexplained issue in how Ordovician craters are distributed, and they put forward a possible explanation for that as an invitation for more study and more consideration from other researchers who might be better equipped to analyze these different aspects. Though this isn't a totally uncontroversial approach either, I think scientists vary a lot in how appropriate they think it is for someone to just throw an idea out there for the community to discuss, or whether they think there's more of a responsibility on individual researchers to ensure that if they're going to put an idea in a scientific journal in print that may be picked up by the broader media or just read by people outside of the field, that they should be confident that they're adding to the body of human knowledge rather than just wasting everyone's time. And to be honest, I can't really be certain what the authors of this paper thought they were doing. They say there's a possibility that Earth may have had rings, but that sort of prevaricating is kind of just the dialect of science. Deeper in the text, they present the statistical analysis as having very clear, indisputable results, and they talk about the ways that climate data could be used to establish more about the nature of the ring, in a way that treats the presence of a ring as basically already settled. Though to be fair, they also make a few geological predictions about potential ring-related deposits that other people could then test with further study, so I don't know. Maybe they do regard this paper as conclusive rather than just an idea they're floating, in which case I guess I do think they've been a bit incautious in their approach and unimaginative in assessing the weaknesses of their own argument. But again, I don't know what kind of resources or time they had to devote to this. And, science is a big field. You're just going to have people like that who are a bit overconfident or they don't think of possible confounding factors. And, peer review is a bit of a filter on that, but it isn't as strict about these sort of things as you might expect. The standards vary quite a bit, actually, but in general, it's kind of just a check on if the process makes sense. Was the methodology properly performed, and does it logically support the conclusions? Reviewers might suggest extra tests or other previous results that the paper should consider and respond to, but they're not like the ultimate arbiters of the truth. When it comes to the interpretation of the results, a lot of the times the onus is more on the community as a whole to decide if they agree with the argument of a particular paper. Again, opinions on this sort of thing vary. Different papers have different standards, and some people have different opinions on how this whole system should be improved. Like, maybe the whole science publishing industry shouldn't be run by the profit motive. I'm just saying. And all of this happens at a very un-Twitter friendly pace, or whatever we're calling Twitter now. As of July 2025, Google Scholar shows 6 citations for the Ordovician ring paper. Mostly just little papers about craters or Ordovician life that mentions the ring idea in passing as a bit of environmental flavor. Then there's one review paper which talks about the causes of Ordovician cooling that brings up the ring idea briefly, only to immediately shoot it down as the cause for the cooling because the timeline just doesn't work out. Ultimately, they think it's mostly just down to the CO2 decline, and maybe the final cooling snap was driven by something like the modern Milankovitch cycles. And then there's one paper talking about how this might relate to TGD theory, which is an acronym defined nowhere in the text, but it seems to propose that Earth has somehow doubled in size since the Cambrian, and so I guess would have crashed into this ring. And the paper also says that stock market crashes are correlated to the passage of Mars behind the Sun because it interferes with the quantum coherence between our brains and Mars's dark gravitational magnetic body. I tried looking around for some more informal responses to the paper from more conventional researchers, but I didn't really find anything. But I don't think it would really matter if there was anything like that. It's not important that everyone has a take on the Ordovician ring paper. If they have issues with the proposal that they think are worth expressing, they'll think it through and write out a detailed response, and this will all get sorted out in the fullness of time. This paper is probably going to get plenty of citations in the long run. I don't think that geology is going to give us any clear answers anytime soon, but climate and astrophysics modelers will probably test out the idea just because it's an interesting puzzle, and even if the consensus turns against the proposal pretty quickly, scientists writing intro sections or review papers love mentioning little oddball theories like this just as points of interest. So, in conclusion, did Earth have planetary rings in the Ordovician? I'm personally leaning against it a bit at this point, based mostly on the issues with the climate data, but there's still possible explanations from that. I'm not going to pretend to have a definitive answer just to appear more confident and authoritative. In 5 or 10 years, we might have more data that either clearly refutes the ring concept or more strongly supports it, or it might be an ongoing debate with lots of papers back and forth, or it might just be ambiguous. The available evidence just doesn't allow for a conclusion, and we'll just have to wait for more data to turn up. I think some people get really uncomfortable with questions just being left open like that. Things that have been proposed and debated, but after all that, still just might be true. But that's science. Certainty requires ambiguity. If you want to be able to say, with confidence, based on evidence and reasoning, that some things are true and other things aren't, then when the evidence isn't sufficient, you have to withhold judgment, rather than trying to force a premature conclusion just so you can make yourself feel better. And I don't just mean stuff like saying, well, this is almost certainly the case, but in principle, we could always find new data. We can never know for sure. No, some things really are just maybe, could be so. No conclusive evidence for or against it, and it might continue to be maybe for a long time, possibly even forever. Alright, that's my first video as world building pasta. Check out the blog if you like. It's a little more speculative fiction focused, but I try and always, focus and teach the science behind the speculative fiction. There's a lot of sort of climate modeling and that sort of thing if you're into that. Hopefully the sound on this video has been okay. It's like 1,005 degrees here, so like all the fans are on. Computer fans going. Maybe we need a ring to cool us down now. That's a real concept actually. Maybe I'll talk about geoengineering one of these days. It's complicated. But thank you for coming. Join the Patreon if you like. It's a fun time there. You get access to the Discord. That's my shilling. Goodbye. Have a good time. One last thing before I go, the very friendly Madeline James has organized a world building festival on YouTube this September from Friday the 5th to Sunday the 7th. A bunch of great channels are participating. So far I have 3 events planned. On Friday, a bunch of us will be joining together for sort of introductory group world building challenge. And then on Saturday in the morning, I'll be doing a sort of speed world building thing where I'll try to create a setting as fast as possible with different ideas people give me. And then a little later, George from Conlangery will be helping me make a naming language for a world I've been working on for a little writing project of mine. There's a bunch of great events from other people there as well. I'll link some info in the description, so go check it out. See you there.